Okay, let's dive into Pytorch and how it stacks up against TensorFlow. Pytorch is a really popular open source machine learning framework. Think of it as a toolbox for building AI models. What makes it stand out? It uses something called a dynamic computational graph. This means you build your model step by step, kind of like constructing with Legos as you go. It's fantastic for research because if you need to tweak things or try a new idea, it's super easy to adapt. TensorFlow, developed by Google, takes a slightly different approach. It uses a static graph. That means the entire calculation is planned out in advance before anything runs. TensorFlow is particularly strong when it comes to deploying models at scale. It's really well optimized for production environments. So, while they both achieve similar goals, Pytorch excels at flexibility and ease of use during development, while TensorFlow shines in deployment. Okay, let's talk about tensors. They're the core building blocks of Pytorch. Think of them as multi-dimensional arrays like spreadsheets, but incredibly flexible. What makes them special is that they live in GPU memory, and Pytorch can automatically calculate derivatives for you, making it perfect for training complex models. A tensor shape tells you how big it is, and its data type specifies the kind of information it holds, like numbers or text. You can create a tensor using functions like torch random, which generates random values. It's that simple. Okay, let's talk about how Pytorch handles automatic differentiation. It's a really clever system. Basically, when you perform operations with tensors, Pytorch automatically builds a graph of all those operations and their inputs. This graph is then used to calculate gradients. It's like tracing back the steps to figure out how changes in the inputs affect the output. You enable this feature by setting requires grad equals true on the tensors you want to differentiate. The system uses forward passes to build up that graph and then backward passes, using the chain rule to efficiently calculate those gradients. The core functions are torch, autograd function, which defines how a function works, and torch, autograd, grad, which is the tool you use to actually get those gradient values. Okay, let's talk about autograd. It's a really important part of Pytorch. Think of it as the engine that drives gradient calculations. When you set requires grad equals true on a tensor, Pytorch starts tracking everything you do with that tensor. As you build up your model and perform operations like multiplying matrices or adding values, Pytorch automatically builds a graph showing how all those things are connected. Then, when you want to train your model, meaning adjust its parameters to improve performance, the autograd backward function comes in. It goes through that graph in reverse, figuring out how much each parameter needs to change based on the desired outcome. It's like a chain reaction of calculations, making gradient-based optimization possible without you having to manually calculate derivatives by hand. Okay, so when it comes to building a neural network in Pytorch, we start by defining our model. We do this using an module, which is like a blueprint for our network. It's essentially a class that inherits from this base class and contains the layers of your network. We create an instance of this class, specifying the architecture, things like how many neurons are in each layer. Next, we define what function will take input data and return predicted output. We then set up our loss function to measure how well our model is performing, and an optimizer to adjust the weights and biases within the model based on that loss. Think of it as a cycle. Feed data into the model, see how wrong it is, tweak its internal settings to be less wrong, and repeat. Okay, so let's talk about what goes on inside a Pytorch training loop. It's really a cycle of improving your model's predictions. First, you feed some input data into the network. That's the forward pass. Then, we figure out how wrong the model is by comparing its output to the correct answer, using something called a loss function. Next comes backpropagation. It calculates how each part of the model contributed to that error. Finally, an optimizer tweaks the model's parameters based on those gradients, essentially adjusting the knobs until the predictions get better and better. We keep repeating this process with different batches of data until our model starts performing really well. Okay, let's get into data loaders and datasets. They're like the dynamic duo when it comes to feeding your Pytorch model's data. A dataset is essentially a way to wrap up all your training or testing data. It knows how to grab individual samples from that data. It has two important methods, one that tells you how long the dataset is, and another that lets you get a specific sample using its index. Now, the data loader does the heavy lifting. It takes the dataset and batches the data for you, which means it gives you your data in manageable chunks to feed into your model. It also handles things like shuffling the data so your training isn't biased, multiprocessing to speed things up, and parallel loading, basically making sure your model gets the data it needs quickly and efficiently. Okay, let's talk about getting your Pytorch models running faster. Moving a model and its associated data to the GPU is crucial for speeding up your deep learning workflows. The easiest way to do this is with the method. You can use it to move individual tensors like batches of images or numerical data or the entire model itself to the GPU if one's available. Just make sure you check for GPU availability first, and then apply. Autograd. Don't forget to move any optimizers and data loaders too, so they can all work efficiently on your chosen device. Okay, let's talk about how Pytorch handles your data specifically, whether it's running on your CPU or GPU. You've got three main tools for this: CPU, CUDA and TO. CPU simply moves a tensor from the GPU if there is one back to your regular computer's processor. It's great for debugging, or when you need to do calculations that aren't supported on the GPU. Next up, CUDA does the opposite. It moves a tensor asterisk onto asterisk the GPU. This lets you take advantage of the GPU massive processing power for much faster computations. Finally, there's TO. Think of this as a more general purpose tool. It lets you specify exactly where you want your tensor to live, either on the CPU or the GPU, using either CPU or CUDA strings or by directly referencing a CUDA device object. So, TO is really just a wrapper around CPU and CUDA, giving you more control. Okay, let's talk about saving your Pytorch models. It's super important to do this so you can reuse them later without having to train from scratch. There are two main ways to save. The first is using torch save, and it saves just the model's parameters, also known as the state dictionary. You'll then need to load that dictionary back into a new instance of your model class. The second way is saving the entire model structure along with those parameters, which is useful if you want to preserve everything exactly as it was. Just remember, when loading, make sure you're loading into the same type of model class. I'll link to the official Pytorch documentation for more details and best practices. Let's dive into saving our Pytorch models. There are two main ways to do it. The first is using model state dict. This method only saves the learned weights and biases of your model, basically all the parameters that were adjusted during training. It's a really efficient way to save just the knowledge, making for smaller files and faster loading times. Now, if you want to preserve everything exactly as it was, including the structure or architecture of your model, then you'll need to save the entire model using torch save model. This saves both the parameters asterisk and asterisk, the definition of your network layers, connections, etc. It's a more comprehensive save, useful if you're distributing the model or want to restore it precisely as it was trained. Essentially, state dict is like saving just the recipe for baking a cake, while saving the entire model is like saving the whole cake itself. Okay, so transfer learning is a really smart way to build machine learning models. Basically, instead of starting from scratch with a completely new neural network, we leverage the knowledge that an existing model has already gained from training on a huge dataset like ImageNet. We pick a pre-trained model, ResNet, PGG, BERT or some popular ones, and then adapt it to our specific task. We usually start by freezing most of the initial layers in the pre-trained model. This keeps those foundational features intact. Then we add a new layer or two on top, a classifier specifically designed for our problem, and train just asterisk that part of the network. Sometimes, after getting things going, you can unfreeze some of the earlier layers and fine-tune them at a really low learning rate to get even better results. It's like giving your model a head start. Okay, let's dive into optimizers. These are the workhorses behind training your Pytorch models. Basically, They adjust the weights and biases of your network to make it better at making predictions. They do this by taking steps in the direction that reduces the error. Think of them like a guided search for the best settings. We've got some popular choices like SGD, which is the original, Adam, which is really good at adapting learning rates automatically, RMSprop and autograd, which are also adaptive but with slightly different approaches. It's all about finding the right optimizer to fit your model and data. Okay, let's talk about crafting custom loss functions in Pytorch, a really valuable skill to have. Often, the built-in losses aren't quite right for your specific task. You might want to give extra weight to certain errors or incorporate some domain expertise into how you measure success. The first step is simply defining your loss function as a Python function, taking the model's output and the true labels as input and returning a single scalar value representing the loss. Then, within your custom module class, you need to implement a forward method. This is where all the calculation happens using Pytorch tensor operations to make sure that automatic differentiation works seamlessly. For example, you might want to use something like focal loss if you're dealing with an imbalanced dataset. The important thing is to ensure your loss function returns only one value per batch and uses Pytorch tensors for calculations. Okay, let's talk about TorchScript. It's essentially a way to turn your Pytorch code into something super efficient that can run really quickly, like almost machine code fast. It's a specialized language built on top of Python and Pytorch. Think of it as freezing your model so you can deploy it anywhere, even places where Python isn't natively supported, or to speed up how quickly it runs when you need it most for inference. It's especially useful if you are deploying your models into production environments. Okay, let's talk about exporting Pytorch models to UNCs. UNCs is like a universal language for machine learning. It lets you run your model on a whole bunch of different platforms. To do this, we use the Torch UNCs export function. First, make sure your model is in evaluation mode and define the expected input shapes. This tells UNCs what kind of data to expect. Then, specify the names for each output tensor, so you know which one represents which part of the prediction. You can even tweak some optimization settings to get a really efficient UNCs model. Okay, let's talk about computational graphs in Pytorch. They're a really important concept for interviews. There are essentially two types, static and dynamic. Static graphs are like blueprints you create beforehand. Every operation is defined upfront. This makes optimization easier but reduces flexibility. Dynamic graphs, which are the standard in Pytorch, build the graph as you go. It's more like a flowchart that adapts to your code. Pytorch's default behavior is dynamically building graphs, offering a lot of flexibility for debugging and experimentation. TorchScript lets you compile parts of your Pytorch code into static graphs when needed, boosting performance during deployment. Okay, let's talk about gradient clipping, a really important technique for stable training in Pytorch, especially when you're working with larger models or bigger batches. Basically, during backpropagation, the gradients which tell your model how to adjust its weights can sometimes get really big, like astronomically huge. This is called an exploding gradient problem. It causes instability. Your model essentially bounces around and struggles to learn properly. Gradient clipping is a simple but effective way to fix this by limiting the size of those gradients. It's like saying, okay, you can only change the weights by this much. Pytorch provides a convenient function called clipGradNorm that does exactly this, scaling down any gradient that goes over a certain threshold. Usually 1.0 is a good starting point. Okay, so let's talk about overfitting, a common problem when building Pytorch models. Basically, your model becomes too good at memorizing the training set and struggles with new data. There are several ways to combat this. Regularization techniques like L2 or adding penalties based on weight size can help keep things simple. Dropout randomly turns off neurons during training, forcing the network to learn more robust features. Data augmentation is also really useful. It's a way of expanding your training set by creating slightly different versions of your existing data. And finally, stopping monitoring performance on a validation dataset and stopping training when you start seeing things get worse. That's crucial for preventing overfitting. Okay, let's talk about getting the most out of multiple GPU when training your Pytorch models. The biggest technique we'll cover today is called data parallelism. Essentially, each GPU gets its own copy of your model and processes a different chunk of data. Think of it like having multiple teams working on the same problem simultaneously. To make this work effectively, you need to wrap your model in something called NN parallel. Distributed data parallel. This module takes care of synchronizing the gradients. That's how all those GPU agree on how to adjust the weights before updating the main model. The key is to ensure each GPU gets a different batch of data during training, which helps with load balancing and prevents bottlenecks. There's also model parallelism, but data parallelism is usually easier to implement for most scenarios. Don't forget to initialize your distributed environment properly using Torch distributed. Okay, let's talk about mixed precision training, a really useful technique for speeding up your Pytorch models. Basically, it's like using a slightly less precise calculator to do some calculations while still getting the right answer. We use 32-bit and 16-bit floating point numbers. Why? Because 16-bit allows us to store our model and data in less memory, letting you train bigger models or with larger batches on GPU that might not have tons of RAM. Pytorch's automatic mixed precision module makes this process pretty easy. It handles the details automatically. It uses a technique called loss scaling to prevent problems with underflow during training and dramatically speeds up your training time. Okay, let's talk about the heart of building models in Pytorch, the NN module class. It's a really important concept to understand. Basically, it's like a container or blueprint for your entire neural network. It lets you bundle together all the different layers you need, like linear layers, convolutional layers, or whatever else, into one neat package. This makes building larger and more complex networks much easier because it handles things like tracking the parameters that get learned during training automatically. It's a super flexible way to build your models. Okay, let's talk about NN sequential and NN module in Pytorch. They both help you build neural networks, but they're quite different. NN sequential is like a simple chain of layers. Just put them in the order you want, and data flows through them one by one. It's great for small, straightforward models. Now, NN module is more powerful. It's the base class that allows you to create custom layers and models with control over their parameters. You manage these parameters explicitly using methods like self-parameters. Basically, NN sequential is good for simple pipelines, while NN module gives you a lot of flexibility when building more complex architectures. Okay, let's talk about those frustrating not-n loss values you sometimes see during Pytorch training. They're a common sign that something isn't quite right with your calculations. First thing to check is for any division by zero. These are the usual culprits behind not-ns. Next, look at your gradients. If they're getting huge, it can cause problems. Gradient clipping is a good tool here. Also, make sure your input data is scaled properly and that your batch size and learning rate aren't too aggressive. Finally, sometimes specific activation functions like ReLU can trigger not-ns if the input values are extremely large, so consider alternatives like leaky ReLU or ELU. Let's talk about callbacks in Pytorch. They are essentially hooks that let you add custom code into your training process at specific points, like the start of an epoch, after each batch, or even when the optimizer updates its parameters. Think of them as ways to monitor and influence what's happening during training. You can use them for all sorts of things: logging progress, saving checkpoints, adjusting learning rates, you name it. To implement a callback, you create a function that takes information like the current epoch number, the batch being processed, the optimizer, and the model itself. You then register this function with your training loop using methods provided by Pytorch's optimizers or by adding it directly to your training loop implementation. Okay, let's talk about Torch, NN. Parameter. Think of it as a special kind of tensor in Pytorch that tells the framework to actually learn its value during training. It's like giving the model the ability to adjust specific weights and biases. If you don't wrap your tensors with Torch, NN parameter, Pytorch won't track how they change, and therefore won't update them during backpropagation, meaning the model won't actually learn anything. You usually see these used within layers like linear or convolutional layers to define the weights and biases. It's a really fundamental concept for building your neural networks effectively. Okay, let's talk about saving Pytorch models. Both Torch Save and Torch Save do the same basic thing. They allow you to store your trained model so you can reuse it later. However, they approach this task in very different ways. Torch Save uses Pytorch's own internal format. It's like saving a file in a specific format only understood by Pytorch. That makes it great for speed if you're running the model on the same machine it was trained on, but it can be tricky to move your model around or deploy it on different hardware. Now Torch Save is cleverer. It converts your model into UNC's, a standard format for representing neural networks. This means your model can run on a huge range of platforms, CPUs, GPUs, even mobile devices, and in the cloud. While it might be slightly slow during inference sometimes, the increased portability and compatibility often make it the better choice, especially when you're deploying to different environments. Okay, let's talk about data augmentation in Pytorch. It's a really important tool when you don't have tons of training images. Think of it as creatively expanding your dataset. By creating slightly different versions of your existing photos or data points, like flipping them horizontally, rotating them, or adjusting the colors, you help your model learn to be more robust and less likely to overfit. It's all about making sure it can handle variations in the real world that aren't perfectly represented in your original data. And don't forget, these transformations usually happen during training. Okay, let's talk about monitoring how your Pytorch model is actually learning. It's not enough to just train it, you need to see if it's making progress. One key thing is loss curves. These show you how well the model is minimizing its error over time. You want to see that loss steadily going down. Alongside loss, track metrics relevant to your task like accuracy or firm score. And critically, always evaluate on a validation set. This will tell you if your model is just memorizing the training data instead of actually learning to generalize. Finally, don't forget tools like TensorBoard, which can make visualizing all that information super easy. Okay, so let's talk about why Pytorch Lightning is such a big deal. It's like a super helpful assistant for your deep learning projects. One of the biggest benefits is that it takes care of all the messy details, things like making sure your code runs on the right hardware and handling looks automatically. This means you can spend less time writing boilerplate code and more time actually designing cool models. Plus, Lightning helps keep your code organized and readable, which makes it much easier to find and fix problems. And if you want to train your model across multiple GPU or computers, Lightning makes the process a lot simpler too. It's all about making deep learning accessible and efficient for everyone. Okay, let's talk about learning rate schedulers in Pytorch. They are super important for getting your models to train effectively. Think of the learning rate like a step size when you're trying to find the lowest point on a mountain. A fixed learning rate can be tricky because it might overshoot or get stuck in local minima. Schedulers help by adjusting that step size dynamically. There are different types. Some reduce it at specific intervals, others multiply it, and cosine annealing uses a cool wave-like pattern to gradually decrease the learning rate. The best scheduler really depends on your data and model, so experimentation is key. Okay, let's talk about how you'd figure out if your Pytorch model is running smoothly. It's not just enough to see a good accuracy score, you need to understand how it's getting there. The first step is often using the built-in Torch profiler. This tool lets you track exactly where your code is spending its time, like how long it takes for data to load and how much processing each layer demands. You can then drill down into specific layers to see which ones are particularly slow. Don't forget to keep an eye on your GPU, make sure it's being fully utilized and not running out of memory. Data loading is a very common culprit when performance suffers, so optimizing that process can make a big difference. And finally, experiment with different batch sizes. Bigger batches often speed things up, but you need to find the sweet spot for your hardware. Okay, let's talk about state dict in Pytorch. It's a really important concept for working with your trained models. Basically, It's like taking a picture of all the learned weights and biases within your neural network, everything your model has figured out during training. You need this to save your model so you can reuse it later, or even load pre-trained weights from another dataset, which is fantastic for things like transfer learning. It also helps when moving models between a CPU and a GPU because it ensures that the parameters are consistent across those devices. Think of it as a convenient way to capture and restore everything your model has learned. Okay, so let's talk about building a custom Pytorch dataset. This is really useful when you have data that doesn't fit neatly into one of the built-in datasets. The key is to inherit from Torch utils dataset. Inside your class, you'll initialize it with any parameters you need like file paths or labels. Then, you need to define two crucial methods, len, which tells Pytorch how many samples are in your dataset, and getItem, which is where the magic happens. This method takes an index and returns a single sample as a Pytorch tensor. I've shown you a basic example, just remember to replace those placeholder comments with your actual data loading code. It's all about adapting to your specific data. Okay, let's talk about freezing layers when we're using transfer learning. Think of it like this. You've got a really smart model that's already learned a lot, maybe it was trained on millions of images. But your new dataset is smaller. If you just start tweaking everything in the big model, you risk forgetting all those valuable general features. Freezing layers helps us do that. We keep the initial parts of the network, the ones that recognize basic stuff like edges and textures, untouched. Then we only adjust the later layers to specialize for your specific problem. In Pytorch, you can control this with autograd. Simply setting it to false on certain parameters tells Pytorch not to calculate gradients through those layers during training. Usually, you'd freeze most of the earlier layers and just fine-tune a few at the end. Okay, let's talk about autograd. It's a super important function in Pytorch training loops. Basically, when you're running through a batch of data, the model calculates how much each parameter needs to change to improve its predictions. These changes are stored as gradients. But what if you want to do multiple calculations for each input in that batch, like maybe calculating some statistics or performing different operations? If you don't reset the gradients between those calculations, they'll all add up. Autograd clears out those old gradients so that each calculation starts fresh and you get accurate updates to your model. It keeps everything nice and tidy during training. Okay, let's talk about batch size and mini-batch. They're closely related but important to understand. Batch size is the total number of examples you feed into your model at once during a single training step. Think of it as processing the entire data set in one go. However, often we don't have enough memory for that. That's where mini-batches come in. A mini-batch is simply a smaller chunk of those examples, like 32 or 64. Using mini-batches makes training more efficient by reducing memory needs and can even speed up the learning process by introducing some randomness into the updates. Okay, let's talk about handling variable length sequences in Pytorch. A really common situation is when you have data like text or time series where each sequence isn't exactly the same length. The first thing we often do is padding, essentially adding a special token, usually 0, to the end of shorter sequences so they all match the longest one in your batch. We can achieve this using Torch, cat, and creating a mask. Another important technique is dynamic padding, where you generate a mask for each individual sequence before padding. Finally, when working with attention mechanisms, we use masks to ignore padded tokens, ensuring they don't influence the calculated weights. Okay, let's talk about the amazing collection of libraries that have sprung up around Pytorch. It's like a thriving community constantly building tools to make things easier. Torch Vision is your go-to for all things computer vision, think image recognition and classification. Then there's Torch Text, which is fantastic for natural language processing tasks such as analyzing text or building chatbots. For audio enthusiasts, Torch Audio provides specialized tools for working with sound data. Pytorch Lightning really streamlines the training process, handling a lot of the complicated details so you can focus on your model. And finally, Scotch lets you seamlessly integrate your Pytorch models into scikit-learn pipelines, super handy if you're already using those. Let's talk about quantization in Pytorch. It's a really smart way to make your model smaller and faster. Basically, we're reducing the size of numbers representing our neural network, like switching from 32-bit floats to 8-bit integers. Pytorch offers a few different ways to do this. The easiest is dynamic quantization, where we quantize activations during runtime, great for models that change shape. Static quantization involves pre-calculating ranges and applying them before running the model, which provides the most performance boost when you have static input sizes. And then there's quantization-aware training, which is a bit more involved but often gives the best accuracy after quantization. Okay, let's talk about J8 compilation in Pytorch. Basically, it's like giving your code a little boost at runtime. Instead of Python interpreting every line as it goes, J8 compiles parts of your model directly into machine-readable instructions much faster. It works by building a graph of all the computations you're doing and then turning that graph into optimized code. This results in a noticeable speed increase, often several times faster than running purely in Python. Keep in mind, though, that J8 is best for functions that behave consistently. They have to be pure, meaning they always give the same result if you put the same input in. Okay, let's talk about TorchServe. Basically, it's like a super smart waiter that takes requests for your Pytorch model and delivers the results. It handles all the tricky stuff behind the scenes, things like making sure your model is always ready to answer questions, optimizing how quickly it responds, and even letting you test out different versions of your model. You'd use TorchServe when you've trained a Pytorch model and need to put it into action in a real-world setting, whether that's on a website, within an app, or somewhere else where people are asking questions of it. Okay, let's talk about why Pytorch is such a popular choice for both researchers and teams building real-world applications. One of the biggest advantages is its dynamic computation graph. It's like having a flexible blueprint that adapts as you go. This makes it fantastic for experimenting with new ideas during research. Plus, because it's so well integrated with Python, using Pytorch feels really natural if you're already familiar with the language and libraries like NumPy. Debugging is also much easier than with other frameworks, which can save a ton of time. And of course, it's built for speed thanks to its support for GPU. Finally, tools like TorchScript help make sure that your models are ready for deployment in production. Let's talk about early stopping, a really helpful technique to avoid your model memorizing the training data and becoming overfit. It basically means we keep an eye on how well our model performs on data it hasn't seen before, specifically a validation set. We track its loss there. If that validation loss starts getting worse, even if the training loss is still going down, it's a sign that we need to stop because the model is starting to learn the noise in the training data rather than the true patterns. We define how long we'll wait for things to get worse before stopping. And as you can see in this example code snippet, we implement this by calculating validation loss after each epoch and checking if it has gone above a certain threshold, usually a small increase. If it does, we halt training. It's all about preventing overfitting and getting a model that generalizes well to new data. Okay, let's talk about gradient accumulation. Imagine you're training a really big neural network, but your GPU just doesn't have enough memory to handle a huge batch size. That's where gradient accumulation comes in handy. It's like doing multiple mini batches and then combining their gradients before updating the model weights. You don't need more VRAM to increase your batch size. You simply calculate the gradients for several smaller batches, add them up, and only update the parameters once you've accumulated enough of those gradients. This can be especially useful when you want to improve generalization, as larger effective batch sizes often lead to better results. Okay, let's talk about getting your data ready for a Pytorch model. One of the most important things is to normalize it. Basically, make sure all your features are on roughly the same scale. Why? Well, if you have one feature that's way bigger than everything else, it can easily dominate the training process and slow down learning. There are a few common ways to do this. Min-max scaling brings values between 0 and 1, great when you know your data's range. Standardization centers the data around 0 with a standard deviation of 1. And if you have outliers, robust scaling is a good choice because it's less affected by those extreme values. Pytorch provides handy functions like torch, min torch, max torch, mean and torch, std to help you quickly normalize your data. Okay, let's dive into how Pytorch decides what numbers to put in those initial weights for your model. It's not just random guesses. Pytorch provides a handy module called torch, and an init that handles this process. The default is pretty smart, but you'll often want to customize it based on the type of activation functions you're using. You can initialize with 0 values, or use something like Savior initialization, which helps prevent those nasty vanishing and exploding gradient problems. Timing and here are other common choices that work particularly well with ReLU activations, a really important consideration when building your networks. Okay, let's dive into some common problems you might run into when training Pytorch models. First off, make sure your data is really clean. Processing it properly is absolutely vital. Then, be mindful of overfitting. If your model is too complex for the data you've got, it will just memorize it. Next, you'll likely encounter vanishing or exploding gradients in deep networks, and tools like batch normalization can help with that. Don't forget about learning rate. Finding the right one is crucial, and adaptive optimizers are worth exploring. Batch size matters too. Experiment to find what works best for your data. And most importantly, always use a validation set to monitor how well your model's generalizing beyond just looking at the training accuracy. Okay, let's talk about dealing with situations where one class in your data is way more common than another. We call that an imbalanced data set. This can mess up your model's performance because it might be biased toward the majority class. There are several things you can do. First, you can try oversampling the minority class by creating synthetic examples using techniques like SMUT. Alternatively, you could undersample the majority class to reduce its size. A really useful tool built into Pytorch is class weighting. This tells the model to pay more attention when it gets a misclassification from the less frequent classes. Focal loss is another powerful technique that focuses on the difficult examples. Finally, you can use data augmentation, essentially creating variations of your existing minority class samples alongside oversampling to really boost its representation. It's important to keep an eye on how your model performs with these changes on a holdout set to make sure you're not just memorizing the training data. Okay, let's talk about detach in Pytorch. It's a really handy function when you need to work with a tensor without affecting its gradient history. Think of it as creating a copy of the data that's separate from the main computation graph. When you operate on this detached tensor, Pytorch stops tracking how those operations contribute to the overall gradient calculations. This is super useful during evaluation or inference. You don't want your forward pass influencing your backward pass. It also helps when moving tensors between the CPU and GPU, preventing unnecessary gradient information being transferred. Okay, let's talk about memory management in Pytorch. We often encounter torch, no grad and torch, enable grad. Torch, no grad is a really handy context manager. Think of it as telling Pytorch, hey, I don't need to keep track of how things change here. Let's just do the calculations quickly without saving any information for backpropagation. It's perfect for when you're running your model on new data and aren't training. Now, torch, enable grad is different. It simply tells Pytorch, okay, these tensors can be used to calculate gradients. It doesn't necessarily mean they will be, but it makes them eligible for the backpropagation process during training. So one disables everything, and the other just turns gradient tracking on. That's the key difference. Okay, let's dive into how you can create custom evaluation metrics in Pytorch. It's really useful when the standard loss functions don't quite capture what you want to optimize. Essentially, you calculate these metrics after each epoch or even after each batch, meaning they aren't automatically integrated into your training loop like a typical loss function. You define them yourself and then compute whatever best describes how you want to evaluate your model. I'll show you some basic example code. The key is to implement your specific calculation logic inside the custom metric function. You track these metrics over time to monitor progress, giving you more granular insights than a single loss value alone. Okay, so let's say you're deep into training your Pytorch model and suddenly the electricity goes out or you need to stop for a while. You don't want to start from scratch, right? That's where checkpoints come in handy. To resume training, first, you load the save state dictionary, all the learned parameters of your model using Torch load. Then, you create a new instance of your model class and initialize it with that loaded state dictionary. It's super important to reset the model architecture, otherwise you'll be starting with a fresh and potentially different model. Next up is the optimizer. You load its state using optimizer load state dict, which keeps track of things like momentum and learning rate history. Finally, just start your training loop again from where you left off. That's usually indicated by the epoch or iteration number from the checkpoint file. Okay, let's talk about Pytorch hooks. They're basically like little helpers that you can add to your neural networks. Think of them as interrupt points within the computation graph. They allow you to step in and change things happening during training or inference. You can register functions called hooks to run before or after specific operations, like a forward pass or backward pass. There are two main types: forward hooks, which happen before calculations, and backward hooks that trigger afterward for gradient tracking. You might use them to clip gradients to prevent exploding values during training, track the values of tensors to help debug your model, or even create completely custom loss functions. It really opens up a lot of possibilities for extending Pytorch's capabilities. Okay, let's talk about backward. In Pytorch, it's a really important concept for understanding how models learn. Essentially, backward calculates gradients, which tell us how much each of our model's parameters contributed to the final error or loss. You can think of it as figuring out, if I tweak this weight here, will the error go down? Now, a really common question in interviews is whether you can call backward multiple times. And the answer is yes. It's totally valid and actually quite useful. You're not limited to just calculating gradients for one loss at a time. You can chain calls, meaning you compute the gradients for one tensor, and then use *** gradients as inputs when calculating gradients for another tensor in your network. This lets you handle multiple loss terms or different parts of the model independently. Okay, let's talk about a really important detail when you're working with Pytorch and training your models: retain graph equals true. Think of it like this: every time you call backward, Pytorch builds a brand new graph to calculate those gradients. That's fine for simple setups, but if you're doing things like gradient accumulation, where you build up your updates over multiple batches, or using really complex models with custom operations, that constant building can get expensive in terms of memory and time. Retain graph equals true tells Pytorch to say, hey, let's keep the original graph from the forward pass so I don't have to rebuild it every single time. It's like reusing a stencil, much more efficient. Just remember that retaining the graph does use a little extra memory, so only use it when you really need to. Got it? Okay, let's talk about weight decay. It's a super common technique in Pytorch to help prevent overfitting. Basically, it adds a penalty to the loss function when the weights of your neural network get too big. Think of it like telling the model, hey, don't make those weights ridiculously huge, keep them relatively small. You can implement this either directly within your optimizer, setting the weight decay parameter, or you can build it into your custom loss function by calculating the sum of the squares of all the weights and adding a term proportional to that sum. The key is to tune the weight decay value, experiment with different values to find what works best for your specific problem. Okay, let's talk about gradients. They're super important when you're training a Pytorch model. It's really valuable to understand how your model is adjusting its weights. First, during the training process itself, we can use Torch, autograd, grad check to double check that our gradient calculations are correct. Think of it as a quick sanity check for any custom layers or loss functions you might be using. After training finishes, you can access those gradients directly through your model's parameters. Just loop through them and look at the values. You might want to normalize them somehow to get a better sense of what's going on. And if you see huge, exploding gradients which can cause problems, gradient clipping is your friend. It limits the size of those changes, helping stabilize the training process. Finally, tools like TensorBoard or weights and biases are fantastic for visualizing gradient magnitudes over time. that gives you a really clear picture of how learning is progressing. Okay, let's talk about computational graphs in Pytorch. Basically, it's like a blueprint for your neural network's calculations. Every layer you use, whether it's a linear layer or ReLU activation, gets represented as a node in this graph. The connections between those layers show how the data flows during computations. What's really cool is that Pytorch builds this graph automatically as you write your code, and it uses it to efficiently calculate gradients when training your model. It's dynamic, which means it adapts as you go, making things super flexible. Okay, let's talk about lazy modules in Pytorch. They are a really clever way to build dynamic models. Basically, Pytorch doesn't create the entire computation graph all at once like some other frameworks do. Instead, it builds it as you go. Lazy modules are wrappers around tensors and functions that mean the actual graph is only created when you need it, usually during backpropagation. This means you can have really flexible models, use memory more efficiently, and build your code in a modular way. Think of it like building with Legos. You add pieces as you go, not the whole structure upfront. Okay, let's talk about how Pytorch deals with operations that don't have derivatives, things like rounding or taking a floor. Pytorch's brilliant autograd system automatically figures out how to calculate gradients for most of your code. But not everything is differentiable. When you run into an operation like rounding, for instance, Pytorch just says forget about it. It skips calculating the gradient for the specific part of the calculation. This means that portion won't influence how the model learns. It's effectively ignored during backpropagation. It's a forward pass only kind of situation. We're only interested in what asterisk is asterisk differentiable. Okay, let's talk about how Pytorch handles combining tensors. We have three main tools for doing this: torch, cat torch, stack, and torch chunk. Torch cat is like putting multiple rows or columns together. It joins tensors along a specific dimension, but they all need to be the same shape except for that one. Then there's torch stack, which adds asterisk new asterisk dimension by stacking tensors on top of each other. Think of it like building a taller structure. Finally, we have torch chunk, which divides a tensor into smaller pieces, creating separate tensors from the original. It's like slicing a cake. You get individual slices instead of just a cut in the main cake. Let's talk about gradient clipping. It's a really important technique to keep your deep learning models from going haywire, especially when training recurrent networks or large models. The problem is that during training, the gradients, the signals telling your model how to adjust its weights, can get really big. If they get too huge, the weights can update in a chaotic way, and you'll never actually train the network properly. Gradient clipping essentially puts a cap on how large those gradients can become. We set a threshold, and if the gradient exceeds that value, it's scaled down proportionally, like limiting the speed of a runaway train. It's super simple to implement in Pytorch, just by clipping the gradients using torch clamp. You'll often find this used when training RNN or large models with aggressive learning rates. There are key parameters you can tweak, like the clip value and how you calculate the norm of the gradient. Okay, let's talk about model evaluation versus training. In Pytorch, your model doesn't behave exactly the same whether it's running a test or predicting something new. When you want to run your model on data that isn't part of your training set, like during testing or inference, you need to put it in evaluation mode. This is done using the eval method. This tells Pytorch that we don't want to calculate gradients anymore, which saves memory and speeds things up. It also sets batch normalization layers to use their pre-calculated running statistics instead of calculating new ones for each batch. Similarly, if you are training your model, then you need to put it in training mode using the train method. This enables gradient calculation so that Pytorch can update the model's weights during backpropagation. Dropout layers also work differently. They randomly zero out activations when in training mode, which is important for regularization. So always remember to use eval when you are doing inference and testing. Okay, let's talk about attention mechanisms. They are really important for making neural networks smarter. Basically, attention allows the model to focus on the most relevant parts of an input sequence. Imagine you're reading a long article and want to highlight the key sentences. Attention does something similar, assigning weights to different pieces of information. We'll see how it works in Pytorch using scaled dot product attention, which is a common technique. It involves calculating scores based on the relationship between a query, keys, and values. If there are areas we don't want the model to pay attention to, like masking certain parts of data, we can use a mask to set those scores to negative infinity before applying softmax, ensuring they get zero weight. Let's break down the code. It takes a query matrix Q, key matrix K, and value matrix V. It calculates a dot product between Q and the transpose of K, scales this by the square root of the dimension of the keys, and finally uses softmax to generate attention weights and then applies these weights to the values to produce an output. Okay, so let's talk about getting your Pytorch models out into the real world, deploying them. It's a really important step, but it comes with its own set of difficulties. First off, you might run into hardware limitations. Big models can be really demanding on resources like GPU and CPU. Then there's model size itself. Large models often mean slower inference times, which isn't ideal for users. Framework compatibility can also be tricky. Pytorch needs to play nicely with the platform you're deploying it on. Don't forget about data preprocessing. You need to make sure everything is consistent between training and running your model in production. And finally, monitoring and logging are key. You need to keep an eye on how things are performing and be able to troubleshoot any issues that pop up as traffic increases. Techniques like quantization and pruning can help manage these challenges. It's all about finding the right balance. Okay, let's talk about handling imbalanced datasets in Pytorch. A common problem is that some classes have far more examples than others, which can lead to a biased model. Torch, utils, data, weighted random sampler is your friend here. It randomly selects samples for each batch, but it gives higher probability to the underrepresented classes. Think of it as giving those rare classes a little extra attention during training. The code shows how to create this sampler using weights and sample indices. Remember to replace the example data with your actual dataset and adjust the weights accordingly. Typically, you'd make the weights proportional to the inverse frequency of each class. Okay, let's talk about pin memory and non-blocking transfers in Pytorch. Key concepts for interviews. Pin memory is like giving a tensor a permanent spot on your CPU. It won't be moved around unnecessarily. This helps avoid those annoying back and forth data copies between the CPU and GPU, which can really slow things down. Now, non-blocking transfers are all about efficiency. They let you move tensors between devices, again, CPU to GPU or vice versa, without stopping your model from running. Pytorch is torch. Move is your friend here. Think of it as a smooth data transfer while the model keeps working. Okay, let's talk about AMP, automatic mixed precision. Think of it as a clever trick Pytorch uses to make your deep learning models train faster and use less memory. Basically, instead of always using the full 32-bit floating point numbers FP32, Pytorch switches to lower precision formats like 16-bit F16 or BF16 for certain parts of the calculation. But here's the catch: F16 has a smaller range, so it can sometimes lead to issues with really big or really small numbers during training. To solve that, Pytorch automatically scales the loss, meaning how much your model is penalized for errors. It also multiplies the gradients, which tell the model how to adjust its weights by a scaling factor to prevent them from becoming too small and vanishing. The key part? Critical parts like matrix multiplications, always use FP32, ensuring accuracy. This dynamic process happens automatically using tools in the Torch CUDA AMP module. It's designed to be super convenient for you. Okay, let's talk about the collate FN in Pytorch's data loader. Think of it as a custom assembler for your data batches. If you have sequences that aren't all the same length, like sentences and text data, or if you need to do some specific pre-processing before each batch, then this is where you come in. The collate FN takes a list of sample dictionaries and returns a single dictionary representing your batch. It's super useful for handling variable length sequences gracefully. Okay, let's talk about how to write unit tests for your Pytorch models. It's really important because it helps you catch any problems early on and make sure your code is reliable. First, we want to test individual parts of the model like layers or functions in isolation. Then, use mocking to mimic things that might change, such as data loaders. Always check your inputs for validity, make sure they're the right size and type. And finally, use assertions to confirm the output is what you expect it to be. Pytest and Unitest are great frameworks for this job. Pytest is especially easy to learn and offers some powerful features. Don't forget to keep testing as you build. Okay, let's talk about two really important tools in the Pytorch ecosystem: Pytorch Geometric and Torch Vision. Pytorch Geometric is all about graphs. It's your go-to library if you're working with data that has connections between things like people on a social network or molecules in chemistry. It lets you build and analyze these graph structures using powerful neural networks. Then there's Torch Vision, which is dedicated to computer vision. That means it provides everything you need for tasks like recognizing objects in images, detecting them, or even understanding what each part of an image represents. Essentially, PyG handles graphs and Torch Vision handles images, both that are hugely popular in the deep learning world. Okay, let's talk about a common question in Pytorch interviews: the difference between BCE with logits loss and BC loss. Essentially, they both help you build binary classifiers. BCE loss is straightforward. It compares your model's probability output after using a sigmoid function to the actual label 0 or 1. It's simpler but can be less stable. On the other hand, BCE with logits loss takes the raw, unsigmoidified outputs from your model called logits and internally applies that sigmoid activation for you. This is generally considered the better approach because it's more robust to numerical issues, especially when dealing with large or small probabilities. Let's talk about multi-label classification, a really common scenario in real-world applications. Unlike standard multi-class, where your model has to pick just *1* correct answer, multi-label means an item can belong to several categories simultaneously. For example, a movie could be tagged as action, sci-fi, and thriller all at the same time. To achieve this in Pytorch, you'll need to adjust your output layer, typically using a sigmoid activation function on each neuron representing a potential label. This gives you a probability score for each label. Then you use binary cross-entropy loss, but importantly, you'll want to consider class imbalance by adding weights using the pos-weight argument. Finally, don't forget to backpropagate and optimize your model. Okay, let's talk about RNN and their siblings LSTMs and GRUs. At the core are recurrent neural networks, which are designed to handle data that has a sequence, like sentences or time series. They work by remembering information from previous steps. However, vanilla RNN struggle with really long sequences because they can forget earlier parts of the sequence. LSTMs were developed to fix this. They introduce these clever gates: input to forget, and output that let them selectively remember and discard information as needed. GRU are a streamlined version of LSTMs, using fewer parameters while still tackling those long-term dependencies effectively. So, if you're dealing with short sequences, an RNN might be enough. For longer, more complex sequences, LSTM is often the best choice. And if you need something fast and efficient without sacrificing too much accuracy, GRU can be a really solid option. Okay, let's talk about handling variable length sequences in Pytorch. Often when dealing with things like text or time series data, we have sentences or data points that aren't all the same size. Some are shorter, others are longer. Pytorch needs everything to be consistent, so padding and masking come into play. Padding is essentially adding a special value, usually 0, to the end of shorter sequences to make them match the length of the longest sequence in your batch. Think of it like filling in blanks. Then, masking tells the model which parts are real data and which are just padding. It's a Boolean tensor: true for actual data, false for padding. The mask is then used during calculations so the model ignores those padded values, preventing them from messing up your training process. It's a really important technique when working with dynamic sequences. Okay, let's talk about creating custom optimizers in Pytorch. It can seem a little daunting at first, but the basic idea is quite straightforward. You start by inheriting from Torch, optimizer. Then, in your init method, you'll define any parameters specific to your optimizer like the learning rate. The heart of the optimizer is the step method. This is where the magic happens. It updates the model's parameters based on the gradients and its internal state. You might also have an optional update state method if you need to maintain any internal variables that change over time, like momentum or variance. Think of it as a way to customize how your model learns. This code example shows a really basic implementation. Okay, let's talk about forward and backward hooks. In Pytorch, these are like special functions that let you peek inside the computation graph and modify things as they happen. During the forward pass, when your model is making predictions, the forward hook gets called. You can use it to do some custom processing before or after built-in operation. It's basically an interceptor for the forward process. Then, during the backward pass, which calculates gradients, the backward hook kicks in. This lets you adjust those gradients, perhaps scaling them down, adding a term, or even defining new ones if something doesn't have a gradient automatically. It's key for things like custom layers and advanced gradient manipulation. Okay, let's talk about Torch, Tensor and Torch from NumPy. They both help you get data into Pytorch as tensors, but they do it in different ways. If you're starting with something that isn't a Pytorch tensor like a NumPy array, then Torch tensor creates a brand new tensor and copies the data over to it. This can be slower if you have huge amounts of data because everything has to be moved around. However, if you're starting with a NumPy array, Torch from NumPy is much smarter. It tries to reuse the existing memory that's already allocated for the NumPy array. It just views the data in the tensor. That means no copying happens at all and is super fast. So, when dealing with large datasets, always prefer Torch from NumPy if you can. Okay, so let's talk about register buffer in Pytorch. Essentially, it's like giving a tensor a special role within a module. It becomes part of the module's state. Think of it as tracking some extra information that helps your model work, but isn't something you're directly trying to learn through training. Unlike weights and biases, buffers aren't automatically updated during backpropagation. They are independent. They are great for things like running averages or normalization parameters, data that influences the output without being part of the learning process itself. Okay, so when you're training really big Pytorch models, the memory usage can quickly become a bottleneck. Think of all those intermediate calculations activation that happen as data flows through your network. They take up a lot of space. Checkpointing is a brilliant way to manage this. It's essentially like taking snapshots of your model state, its weights, and those crucial intermediate activations and saving them to disk. When you resume training, Pytorch doesn't need to hold everything in memory all the time. It just loads the most recent snapshot and recalculates what's needed on the fly. This dramatically reduces the amount of RAM your model needs, letting you train larger models with bigger batches and ultimately speed up the whole process. Okay, let's talk about building a GN in Pytorch. A generative adversarial network is all about competition between two neural networks, the generator and the discriminator. The generator's purpose is to create new data that looks like the real thing, usually images, starting from random noise. Think of it as an artist trying to mimic a master painter. Then we have the discriminator, which acts like an art critic. Its job is to tell the difference between genuine artworks and the generator's fakes. We train them by having the generator constantly try to trick the discriminator, and the discriminator continuously improving at spotting the forgeries. It's a really cool iterative process. We use specific loss functions that guide this competition. To recap, we have our generator making fake data, the discriminator judging it, and then updating both networks based on their performance. Okay, let's talk about softmax versus log softmax. They both help us turn raw scores into probabilities for classification tasks, but there's a crucial difference. Softmax directly calculates those probabilities by exponentiating the input scores. However, this can cause problems if your scores are very large because you might run into numerical issues like overflow. Log softmax, on the other hand, takes the logarithm of the softmax result. This is much more stable, especially when dealing with big numbers, and it's often a better choice in practice. Pytorch even provides a function specifically for this. Okay, let's talk about dropout. It's a really clever way to help your neural networks avoid getting too specialized and overfitting the training data. Basically, during training, dropout randomly turns off some of the neurons in each layer, like flipping switches on and off at random. This forces the remaining neurons to become more robust and learn more general features. Pytorch makes it super easy with its dropout module. You just specify a p-value, which is the probability of dropping a neuron. Remember to set it to true during training and false when you're evaluating or testing your model. Okay, so when we're training a Pytorch model, it's really important to keep an eye on how things are going. We want to track metrics like our loss and accuracy, basically how well the model is learning. There are a few ways to do this effectively. The easiest might be using Torch Utils Tensor Board. It's a handy tool that gives you a nice web interface to visualize your training progress. Alternatively, for simpler setups, you can just use Python's built-in print function to log values directly to the console or a file. And if you are using Pytorch Lightning, it has integrated logging features. You'll want to focus on metrics like loss, accuracy, and maybe even things like your learning rate and training time per epoch. That way you can really understand what's happening during training. Okay, let's talk about label smoothing. It's a clever trick we can use when training our neural networks for classification. Basically, instead of telling the network exactly what the right answer is, like with one-hot encoding, we slightly soften those labels. Imagine you're trying to identify an image as a cat. Normally, if it is a cat, you'd give it a perfect score of 1. But label smoothing says, okay, maybe it's slightly a dog too, let's give it a tiny bit of probability for that. This helps the model avoid getting overconfident and learn more general features, leading to better performance on unseen data. Okay, let's talk about batch normalization and layer normalization. Both are fantastic tools for making your Pytorch models train better. Think of batch normalization like this. It takes the average value and standard deviation asterisk within a single batch asterisk of data and uses those to normalize each activation. It's great for things like convolutional layers where the inputs tend to be pretty consistent from sample to sample within that batch. Now, layer normalization is different. Instead of looking at batches, it looks at asterisk each individual data point asterisk how its features are behaving on their own. This makes it really useful for recurrent neural networks or situations where your data doesn't have a nice, regular batch structure. The key takeaway is that batch normalization uses statistics from the whole batch, while layer normalization uses statistics specific to each sample. Do you want me to delve into any of these concepts in more detail? Okay, let's talk about learning rate warm-up. It's a really useful technique when you're training deep learning models. Essentially, we start with a low learning rate and gradually increase it over the initial steps of your training process. Think of it like gently warming up an engine before full speed. Why do we do this? Well, early in training, the gradients can be noisy and unstable. A high learning rate at the beginning might cause the model to overshoot its optimal parameters and bounce around wildly, making convergence harder. By gradually increasing the learning rate, we allow the optimizer to find a more stable starting point and improve the overall training process. Let's talk about weight normalization. It's a really handy trick when you're training big neural networks. Basically, it's like giving each weight in your model a little nudge to keep its values within a reasonable range. Think of it as preventing those gradients from going haywire and causing the whole training process to become unstable. It helps the network learn faster and more reliably by making sure that updates aren't too huge or too small, and can even help prevent overfitting. Okay, let's talk about preventing those runaway gradients. Sometimes when we're training deep neural networks, the gradients can get really big, like explosively big. This leads to unstable training and makes it hard for your model to learn effectively. Torch and then Utils clipgrad norm is a super handy tool that helps us control this. It's essentially saying, hey optimizer, I want you to keep those gradients from getting too huge. You just give it the gradients, tell it what kind of norm to use, usually 2, and set a maximum limit. It'll then scale down any gradient that goes over that limit, making sure things stay stable during training. Okay, let's talk about embedding. It's a really important component in many NLP models. Basically, it acts like a super smart dictionary for your text data. Instead of dealing with raw words which can be tricky for computers to understand, we use numerical indices to represent each word. The NN embedding layer takes these indices and transforms them into dense vector representations. These vectors are the word embeddings that capture the meaning and relationships between words, allowing your model to actually understand what it's reading. It learns how similar words are through training, so a good embedding layer is essential for building effective NLP models. Let's move on to discussing how these vectors are actually created. Okay, so when you're asked about visualizing feature maps from convolutional layers in a Pytorch interview, it's all about understanding what the network is seeing. Think of these feature maps as highlighting areas within an image that are important for making predictions. There are several ways to do this. GradCAM is really useful for showing why the network made its decision by focusing on specific regions in the input. Guided backpropagation gives you a bit more control over how you're looking at things, and just directly visualizing the feature maps themselves can be surprisingly helpful, especially if you normalize them to make them easier to read. Let's talk about how to use the Pytorch profiler. It's an invaluable tool for debugging and optimizing your models. Basically, you start by importing the Torch profiler module. It's available in newer versions of Pytorch. Then, you configure it by setting things like what events you want to track, how frequently you want samples taken, and even the format you'd like the results in, like a JSON file or a flame graph, which is really useful for visualizing the data flow. Once configured, you just run your model code, and the profiler automatically collects information. Finally, you analyze the report. It breaks down everything by event type, highlighting the parts of your code that are taking up the most time or using the most memory. Using this info can help you pinpoint bottlenecks and make targeted improvements to get faster training or inference. Okay, let's talk about distributed data parallel versus data parallel. They both help train your Pytorch models faster by using multiple GPU, but they do it in fundamentally different ways. Data parallel is like having multiple copies of the same model, each working on a slice of your data. It's easy to set up, but as you add more GPU, things start to slow down because they have to constantly communicate and copy data. Distributed data parallel takes this a step further. It actually synchronizes gradients across all those GPU using something called all-reduce. Imagine each GPU calculates its own gradient, then they come together and evenly split the result. That's how DDP works. It's much better at scaling to larger teams of GPU. So, if you have a small data set and just a couple of GPU, data parallel might be fine. But for bigger data sets or more than 3 GPU, distributed data parallel is definitely the way to go. Okay, let's talk about quantization in Pytorch. It's a super important technique for making your models run faster and smaller, especially on mobile or embedded devices. Essentially, we're shrinking the numbers representing our model's parameters and activations. There are two main ways to do this: dynamic and static quantization. Dynamic quantization happens during inference, meaning as you're running the model to make predictions. It's really flexible because it adjusts based on what data is coming through, but it can be a little slower. On the other hand, static quantization is done ahead of time, either during training or after, and we predetermine the best way to represent those numbers. That makes it faster at inference, but you'll need some calibration data to help set things up correctly. Okay, let's talk about curriculum learning, a really smart technique for training neural networks. It's based on how we humans learn, starting with the basics and building up to more complex challenges. In Pytorch, this means carefully managing the data you feed your model over time. We can use techniques like selecting only easy examples initially, or adjusting the loss function to give more importance to simpler data points early in training. Another approach is progressive curriculum learning, where we introduce new concepts one at a time, building on what the model already knows. Don't forget that this often needs some experimentation to find the best strategy for your particular problem. Okay, let's talk about reproducibility in Pytorch. It's absolutely vital for making sure your experiments are consistent and reliable. The core idea is to eliminate randomness from the equation as much as possible. That means seeding everything that uses random numbers, Python's built-in random module, NumPy, and of course, Pytorch itself. Setting these seeds ensures you get the same sequence of random numbers each time you run your code. Beyond that, it's a good habit to track your code with version control like Git so you can go back if something goes wrong. Also, make sure all your dependencies are pinned in the requirements file. Condat or Python are great for managing these and preventing issues caused by different versions of libraries on different machines. Finally, storing your experiment settings and configuration files helps keep things organized and prevents accidental changes during runs. Thank you for watching.